All right. Hello, everyone. Welcome to this first Monash Software Systems and Cybersecurity seminars. So this will be the first ever talk of this new extended series, and we are happy to have it in person. And today we are welcoming Joel Kuepper from University of Adelaide. So he studied applied computer science in Germany with Hewlett-Packard from 2013 to 2019. And recently he commenced his PhD in 2020 at University of Adelaide and focusing on automatically optimizing the performance of cryptographic implementations. And so far his tool CryptOpt can generate provably correct side-channel secure implementations for elliptic curve cryptographic primitives, which can outperform off-the-shelf compilers significantly and are on par with handwritten assembly codes. And today's topic will be on this tool, CryptOpt. And without further ado, I'll hand it over to John. Thank you.
Thank you very much, Mohammed, for the introduction. Yeah, I am a PhD student, and I've been working on that project for the last almost 3 years. Started in March 2020. I got the last plane into Australia, so I'm very happy that I was able to do all this. If there's any questions, please just feel free to ask these questions, because I'm more of a interactive person. Otherwise, you would forget these questions anyway. Okay, so I would like to talk about CryptOpt. This is a little bit of the outline. I would like to motivate this project a little bit. Then our idea how to solve this problem, where we can apply that, and a couple of results. And then if we have time, I got some extras. So let's start. So if we look on a graph where the speed of the generated code is on the y-axis and the automation degree of the tool used to generate that machine code is on the x-axis, then compilers are somewhere on the lower right-hand corner. Providing a high degree of automation, you just press the button, it compiles, and then out comes your machine code. But the speed is not necessarily optimal. So the code that a compiler produces is not particularly fast. Whereas humans on the upper left-hand corner, which are able to optimize handwritten assembly, is usually pretty fast, but unfortunately, humans are not yet automated. So with our CryptOpt project, we're trying to push the upper right-hand corner. So let's see how far we can push this. So why are compilers bad? Compilers can compile very complex and optimize very complex programs. And with complex, I'm talking about you have some input language, which usually involves control flow and maybe file input output, integer arithmetic, floating point arithmetic, and a lot of other stuff. And the output of a compiler is then usually one particular machine code for one architecture, for example, ARM for your phones, or by these days also laptops and notebooks, or other architectures. And what a compiler essentially needs to do is 3 things. That is instruction selection, instruction scheduling, and register allocation. Instruction selection means, okay, I have one operation, multiplication. But for example, for Intel architectures, there's multiple ways to implement this particular operation. So I can use any of these instructions depending on the context and the operands that I have. So the compiler needs to decide when to use which. Then we have instruction scheduling, and that deals with the fact when to issue which operation. So for example, if we have x equals a plus b and y equals c plus d, the compiler is free to move them up around, and it's free to schedule one after the other, and that can have performance impacts. And the last step is typically register allocation, which pretty much just deals with the fact which data goes when into which registers, and when do we spill that back to memory if we don't have enough registers. We found that if we have a moderate subset of these compiler tasks, if we only consider integer arithmetic on Intel architectures, we think that we can do better. So let's see, what is our idea? How do we try to make that better? Our idea is essentially, instead of compiling the traditional way, we cast compilation as a combinatorial optimization problem. So what does that mean? And then we generate a fast solution from using these techniques. And in order to be correct, we have, for the general case, we just have test vectors that we compare our solution with a C compiled generated solution and see whether random input gives the same random output. For cryptography, that I'm talking about a bit later in this talk, we also want to, additionally to these test vectors, we want to prove the equivalence with some cryptographic specification that we're trying to implement. So what is the combinatorial optimization problem? Let's look at it formally. We have I, which is a set of instances, and given one set of these instances X, we can define a finite set of feasible solutions, which are actually solutions for that particular instance. And then if we have that set of instances and a feasible solution of that problem, then we can have a function M, which denotes the measure, so how good is that solution out of the set of feasible solutions. And then we have a goal function, which is either we try to minimize or maximize this measure of Y. So that sounds a bit mathematical. So let's see how we apply that to our problem. So our set of instances is, for example, the multiplication modulo one particular prime that is used in cryptography. Maybe you've heard about the curve 25519. That is, its field multiplication is based by multiplication modulo this prime. So this is our set of instances. The next thing is that we have this set of feasible solution, and this is all our different implementations. So we have the specification, but then there's different assembly programs that actually implement that specification, as I said, with different register allocations, different scheduling, and so on. Then we have our measure function, and that is, in our case, we just measure simply is a bit an understatement. We try to measure the CPU cycles which one particular implementation needs to take, and we try to minimize that measure of CPU cycles. So again, to summarize, we have multiplication, we implement that somehow, and we measure the CPU cycles, and we try to minimize that. So let's see, how do we optimize based on this approach? We have our input, which is the specification, and we generate some code from this input specification. We then mutate that particular piece of code and then have a mutated piece of code. And then we compare the runtime of these two pieces of code. And when you compare runtime, you usually have a faster code and a slower code. So one of them will be faster and one of them will be slower. We just simply discard the slower code and continue with the faster code. We reduce the predefined budget a little bit, by one actually. And if we still have some budget left, we continue with that faster code in our next iteration and iteratively continue doing that until the budget is used up, and out comes a fast x86 assembly. Please note that this is a data flow graph and not a control flow graph. So the data flows through the code. We compare the runtime, and we just take the faster code and put it back into our input as the code.
Like a hill climbing algorithm sort of for this compilation?
Yes.
Beautiful. Okay.
So we start just randomly. So this first generation of code is randomly. We just start randomly, and then we randomly mutate. And I'll come to what we can mutate in a little bit. So we start randomly, we mutate randomly, and compare these two random instances. And if our mutation turns out to be beneficial, as in less CPU cycles, we keep that. And if not, we just discard that and try again.
Can I also ask a question?
Yes, please.
So, is there, I guess, a chance that you might get stuck at a local maximum and not reach the? Okay. So you just stop at the local maximum and you don't try to kind of fall back and.
So far, so in the moment, in the current implementation, we just stop whenever the budget is used up, and then we are stuck somewhere. And if that's a local maximum or it is obviously or it's hopefully a local maximum, how we deal with that, I'll come to that later. Yeah. So let's see an example of how we cast this compilation problem into an optimization problem. Our example is a very contrived example, so I can show how it works. So we want to calculate this expression, x times y plus z squared plus y. Doesn't really matter what that is. The point is we want to implement that. And this is our specification, but there's no such instruction which exactly calculates that. That means we need to calculate that in software. So we see that we have our inputs here, z, y, x, and so on. And we have our operations, multiplication and addition in this case. So we combine these inputs and intermediate results into our output such that we get the lower limb and the higher limb of our result. These are all 64-bit limbs. So from this specification, that is our specification, how we implement this particular problem, we generate a data flow graph. And now we see that it is actually not that complicated. We have our multiplication addition up here. We have, this basically shows how we want to implement that. The next step is to implement that in a program. But the problem is that we can't issue two instructions at the same time because we only have one instruction stream. So what we need to do from this data flow graph is a topological ordering, which is an ordering of these nodes, of these operations, such that the data just flows in one direction, which is in this case downwards. So this is one such ordering, such topological ordering, and we could go ahead and implement that. We do notice, though, that multiplication 1 and addition 1 do not share any data. So that means that we are free to start with multiplication 1 or addition 1, or even put the multiplication 1 in between here. That's what I'm illustrating with these bars on the side. So addition 1 needs to be before multiplication 2, but can be either at the first or the second spot. So we have a little bit of a freedom there. And if the expressions get larger and larger, as we do for cryptography later, then this is not a trivial task. Let's remove all that clutter and stick with that particular one instance that we're trying to implement now. So I've said that the next step is that a compiler needs to do instruction selection. So let's select a couple of instructions. So we have our operations on the left side, and we have some assembly instructions attached to these operations. And now it's just a matter of reading top to bottom to generate some code. So this is our code based on this particular ordering with this particular instruction selection. It's not too important what exactly these instructions are. The point that I'm trying to make is we have this intermediate or this internal representation of order and instructions, and we can generate code from that. The next step is we can mutate. This is the mutate step that I've shown earlier. So in this case, I have two mutations. The first one is to mutate the instruction selection from ADCX to add. And down here, we've seen that we can change the order of add 3 and add 4. So let's do that, and then generate some assembly code from that second representation. Again, it's not too important which instruction change. The important thing is that they change, and that in this particular instance, because it's quite contrived, I must admit, we can 1, 2, 3, 4, 5, 6. We can remove 6 instructions from this program and still get the same implementation. And that is quite interesting. Although it's also very important to know that this is not necessarily faster. It's less instructions, yes, and the computer technically needs to do less things, but it's not necessarily faster because we use different instructions, and different instructions can have different impacts on the CPU pipeline and a lot of different things that we have no idea about, that Intel or the manufacturers wouldn't tell us because it's intellectual property or they don't know themselves. So let's see, so that's all good and nice. So let's see where we can apply that. Yes, please.
Ask a question. There's a question in the chat.
Yes, please.
It's from Ningluo. At what level the code is written? If it's in a high level language, how do you mutate? I guess you kind of partially answered that.
I'll come to that in a second. We currently pass a JSON specification, which is well defined, and we generate an assembly file pretty much. So we don't need to invoke a different compiler. We only need to invoke a assembler.
Okay.
I hope that answers the questions. Otherwise, I'll come to that back later. Yeah. Is there any more questions?
No, that's
okay. Okay, then let's quickly recap what we've just done. We took compilation of straight line code and cast it as a combinatorial optimization problem. We then used genetic improvement. That's the part that we've seen earlier in that mutation, iteratively mutation and measure to solve this problem. And by doing that, we can exploit hardware properties without even knowing them. So we just try random things and we don't need to model the CPU in any way. So we just run it and see if it's faster, and if it is, then we exploit that property, whatever that may is. That can be instruction decoding, that can be instruction alignment, that can be cache collisions, anything. But we don't care. So let's see where we have long stretches of straight line code that we try to optimize, where we actually care about 5% of performance that a compiler cannot generate. And that is cryptography. We have large stretches of straight line code with mostly arithmetic. So we've done a case study, and that case study starts with fiat cryptography, which is an MIT project from the Computer Science and Artificial Intelligence Laboratory, CSAIL. And this project exists since 2019, and it is pretty much essentially it generates provably correct cryptographic field arithmetic. So that means it generates C code to multiply big numbers, as we've seen earlier with the curve 25519 example. And these are between 100 lines of C code up to 500-ish lines. They also generate code in different languages like Go and Java, but we don't need to do that now. With our project, CryptOpt, we extend the proofs to assembly so that C code that they have is provably correct, but then you need to, one need to invoke a C compiler to compile that to machine code, and you need to trust that C compiler. With our project, we extend that to assembly, and the way we do that is the following. We see the blue box. That is the optimizer, as I've shown that before. We've actually done 2 case studies, but I'm not going to go into the second case study. So let's look on the left side. We have fiat cryptography, and the input is some prime number, so the 2 to the 55 minus 19. It generates an internal representation and generates some intermediate representation. And we feed this intermediate representation into CryptOpt, then do all our optimization. Out comes our fast assembly, and then we feed that back into fiat cryptography, and there we have a assembly parser, and then we symbolically execute both these programs, and we check whether they are actually the same. And if yes, then we are provably correct on the assembly level. So there's 2 points to this. On the one hand, we have the performance, and on the other hand, we have the correctness. Let's look at the performance first. One example is this, the psycp434 square function, which is a square operation based on the psycp prime. Not too important what that is, but just for reference. We've run the optimizer on this particular 10th gen CPU, and we compare against GCC in the latest version. So what we see here on the left side is the relative speed up against this GCC compiled version. And on the x-axis, we see the mutations. So 100 mutations. Please note that this is a logarithmic scale. And we see here that we start after the 10th mutation, that our performance is a bit slower than the version of GCC, and in this case around 90% as fast. But when we optimize, we get better until we reach on par, and then we are slightly faster. The thing is that we start randomly, and if we run that again, we will have a lot of these traces, and we don't really know where our best one is. So we randomly start in our landscape, in our configuration space, and we turn that into CryptOpt's advantage by just starting at a lot of different things, evaluate that for a bit, and then take the best one and run that for more mutations. So let's squish that and continue with the best approach, and then we see that we can actually get around 60% faster than what GCC would have produced. So that's quite nice. Let's look at the correctness part. So I said, extend the correctness proofs to assembly. How do we do that? We build execution engines in fiat cryptography, or fiat intermediate representation, and in the assembly. And then we symbolically execute all these, both of these programs, and we see how the input symbolically flows through the registers in memory and heap and stack. And then we see whether the output is equal, and then we have a provably correct implementation. To do that on a scalable level, we borrow E-graph structures, which are commonly used in SMT solvers, which is basically just a graph of common nodes. And if another node comes in, we can reuse old nodes. And that way we can scale this up. Any questions so far? Yes, please.
On that part, so what are these nodes, and what are the things coming into these nodes?
So the nodes that are coming in are the nodes that we have seen in the data flow graph earlier. Mm-hmm. So we have this, and we generate. So if we could imagine that data flow graph from earlier, then this is already an E-graph structure. And now we read one instruction from the assembly and see, okay, this is reading data from Z or whatever that was. And we can add this first instruction node, and the edges from that node will fit into the same edges in that data flow graph.
Okay.
And then the next instruction comes and we reuse these nodes. So instead of generating that graph and keep adding nodes, and then it just exponentially grows too big, we reuse these nodes. I have a backup slide, so maybe that one explains it better. Yes, please. I'll comment about that in the performance results section. One second. Anything else? Beautiful. So let's see. If we look back to that graph, let's see where fiat is. Fiat still needs the compiler, but it does generate at the time of publication. Sounds like punishment. No, sorry. At the time of publication, fiat was generating the fastest known C code for these particular primitives, which is quite impressive. Yet they still needed to use typical off-the-shelf compilers to compile that to machine code, obviously. So with CryptOpt, it's a bit hard, because for some primitives we do very good, and for a handful of primitives we don't do that good. And that also depends on the machine that we're actually running on. So let's see. Let's see what we've done in our performance evaluation. So on the left side in this table, we see the different curves or different primes for these particular curves that we generated the multiplication and field multiply and field square operations for. These, so the most known maybe are curve 25519 and P256, which is used in the TLS standard, and probably the SEC P256K1, which is the Bitcoin curve. So every Bitcoin signature needs field arithmetic in that particular field. If we look at one of these comparisons, we see that, so these numbers represent geometric means over 8 particular platforms, out of which 3 were AMD platforms and 5 were Intel's. And a 1.19 means that our code, on average, is 19% faster than what Clang would have produced. And for GCC, we are 14% faster, and so on. If we fill out that table, we see that we are better, which is blue, on most of these curves. For this curve 448, it's a very large curve, and we assume that our optimizer hits their bottleneck there somewhere by not being able to measure the impact of one particular mutation over a large stretch of instructions. So that's what we assume.
Is assuming that that CryptOpt is starting from exactly what Clang and GCC give it?
No, we do not use the machine code from GCC to start CryptOpt with.
Gotcha.
So what we do is we let Fiat generate a JSON specification of the program. We feed that, we read that, we generate our assembly and run that. And on the other side, we let Fiat generate the C code, compile that with GCC and Clang, and compare how many CPU cycles each takes. Gotcha. All right. Which also means that our trusted computing base is not dependent on these off-the-shelf compilers, which always change in every version. So let's see at the state of the project's state right now. Our strengths are we can use common expression elimination, also known as CSE, which means if we have A+5 here and A+5 here, we don't need to recalculate, we just use that. That's a quite commonly used technique. We have strength reduction, which means we know that 2 times x is the same as x plus x, which is the same as x shifted to the left for 1 bit. So why am I bringing this up? This is the instruction selection part that I mentioned at the beginning. So instead of using always one instruction for one particular operation at one particular point, CryptOpt is able to use the multiplication somewhere here and the addition here and the shift here, which distributes the load across the execution units inside of the CPU, or potentially. Typical compilers, on the other hand, they have pattern matching rules and say, okay, usually a multiplication is slower than an addition. So I always replace the multiplication with an addition. However, we notice that sometimes it works, sometimes it does not. It usually works. Sometimes an addition somewhere can be better than a multiplication or vice versa. So we just randomly try these instances. Whenever new hardware comes out, compiler manufacturers typically try to reverse engineer that, try to see how does the instruction decoding change, how does cache lining, how does all these things affect each other, and try to optimize for that particular hardware again. We, on the other hand, do not need to do that. We have our project right here, and we can just run that on new hardware and have fast code, essentially. And that also includes microcode updates. So whenever a microcode update for a particular machine comes along, we can just run it again and see whether we're fast or not. Because we're dealing with cryptography, it may be interesting, how are you dealing with side channel problems? And the answer to that is, we are inherently constant time because the code that we get from Fiat is constant time because it does not branch on secrets, neither does it have secret dependent memory accesses, and neither do we emit these instructions. So we use conditional moves to implement phi nodes, which are known to be, or which are believed to be constant time until someone finds a bug somewhere. So we don't need to think about that too much. A couple limitations we currently only deal with straight line code, which is sort of a limitation, sort of not, because applied to cryptography, that's not a huge problem. And this is a limitation because we can generate the data flow graph only efficiently from straight line code. If we have jumps, we don't necessarily know how the data flows, so we can't use the entire graph and implement that. We do not support vectorization yet because that is known to be a hard problem. And for cryptocode, where we only have integer arithmetic, vectorization does not apply that much, especially for set-rated implementations where you can't use vector instructions in the first place because you lose the carry bits. So it's not too much of a problem. Another limitation could be the runtime. It takes, depending on the machine that we're using, we use little NUCs and the latest, greatest AMD machines, on which one all the curves that I've shown earlier, which are 9, I believe, takes like 1.5 days to 3 days, depending on the machine, to generate all of them with that computational budget that we've shown earlier. If I'm only interested in one particular curve, I could run that, longer or less, or whenever I'm satisfied or convinced that this is a global maximum minimum. And we currently only support the Intel instruction set architecture, which is also not too much of a problem because this is where most of the uncertainties lie. So we have different instruction lengths, we have different instructions to do the same thing. There's a lot of flexibility that compilers currently can't really handle. So we expect less of a performance benefit from other architectures. Let's do a bit of the future work. We could also try to manipulate the data flow graph itself. So if we have something like AY plus YZ, we might as well add these two together first and then multiply by A, which may or may not be beneficial, but that's also quite complex. As I said, we may target ARM in the future, or this project could target ARM in the future, or we could look at different input, like matrix multiplication, which is often used on graphics card and in neural networks and artificial intelligence and stuff like that. And then we have symmetric ciphers. So far, we have only looked at modular arithmetic, which is used in key handshakes and signatures, and not for symmetric ciphers. We could look at post-quantum a little bit more, or we implement hash functions. On the optimization side, we could use different encodings to encode the exact same instruction, which is another entire field that could lead to CPU pipelining effects because of instruction decoding and other opaque properties of the CPU. On the optimization side, we could also try multiple mutations per evaluation. So we've seen that too. I've changed the implementation, the instruction for one operation and the order at the same time. Usually that happens one by one. Using multiple mutations is a double-edged sword in the sense that it may have benefits and it may have, so that we have two good operations that are being chosen to be kept in the implementation. It could also be that we have one bad mutation that outweighs the good mutation that we have somewhere different, and then this entire thing will not be accepted. Or it could also be that we find one mutation that only works in the combination with another mutation, which we then would take, or vice versa. So it gives a lot of noise into the optimization. And we've seen that so far we do quite well. So this is kept as future work. And the last thing that we could do is genetic recombination, in the sense that we have one and we don't mutate, but we have another one from maybe the bad part of the bet and run, as I've explained earlier, and combine these somehow. But this is also not trivial because we need to maintain correctness. So if there's any questions, then I'm happy to answer them. Otherwise, I could go into a little bit more technical details. And other than that, thanks for your attention, and I hope you've learned something. Thank you.
Any questions from the room?
Please.
So you guarantee that you're meeting the specification because it's always some kind of permutation of this graph of precedence relations, etc., right?
Yes.
But you don't do anything specific about pipelining yourself. You just rely on the underlying assembler to well, you don't have any control, or you don't look at those. You don't try to understand what's happening in the black box of your CPU. So one question from me is then, is it a tiny piece of code? How do I check that it's faster? Because if I run it and it's only a tiny piece of code, I can't run it in 1 million loops or something.
Yes.
How do I detect that it's faster?
Good question. So we adapt the R3 validation, which is from Gecko 2020. Essentially what they did is they restarted and tried to reset a mobile phone in the context of energy measurement. So they observed, okay, if I measure the energy now, it's different than tomorrow and day after tomorrow. So what they essentially did, or what we try to adapt from there, is that we try to measure randomly in a rotated fashion. What that means for us is that we first have one piece of code. Our goal was to find out which one of these two pieces of code are faster, right? So we take these two pieces, put them into memory, and run one, and then randomly choose one to run, measure the time, run, measure the time, run, measure the time. Why do we do that randomly? In order to decrease the effect of branch prediction or predictions in general, or cache set interference. That's why we compare them randomly. The second thing that we do is we found that we have a fixed granularity timer, which is CPU cycles. And these CPUs these days, they can execute multiple instructions in one cycle, and it's all over the place, essentially. So what we do is we have an idea of a cycle goal. So we want to measure the function in the range of around 10,000 cycles. And that means that we run one particular function, not just one time, but I think we start with around 500 times, and then automatically adapt that 500 times to converge around 4 significant digits. So longer stretches of code will then run maybe 10 times, and a tenth of that code will run 100 times, such that we can measure around 4 digits of significance. And we found that this is a very good trade-off between running time of the optimizer itself and granularity that we find a good mutation in the first place. Does that sort of answer your question?
So you're not running the actual application, just running it like the same inputs 100 times.
We change the inputs every time we choose a different implementation to run. We run, and running one implementation means a loop of whatever I said, the batch size, we call that a batch. We just run that in a tight loop, yes. So we take the measurement beforehand, run the tight loop, and take the cycle count again.
But if I took the piece of code and I insert it into a loop, and I take a piece of code and I have it in an application, they may not run at the same speed. Right?
Correct. So the application of these functions that I'm trying to optimize, they are being used in a so-called scalar multiplication, which is comprised of point operation, which is comprised of field operations. And I'm trying to optimize here. So the point operations will use the field optimizations, not in a loop, but repeatedly with different input. So the example here is not too bad of an example. If we imagine this to be our implementation that we try to implement, that's our point operation, then we have multiplication here, and it actually is pretty representative, to be fair. So no, it's not running in a loop, but for our experiments, it turned out to be sufficient enough to compare that in a loop.
But I mean, you have experiments where you now run the actual application with your code versus the original code, and you can see it.
Yes. For that, depends on the machine on which we run the experiment. For some implementations, we are better than handwritten assembly, which is sort of the upper bound that we had ourselves. For some, we are slower than the handwritten assembly, but way faster than the machine code. Machine code generated by the compilers. So it depends. Also, and that is in the context of a scalar multiplication, which is the dominant part of the digital signature that is being used everywhere, or the handshake. Yeah. So yes, for our experiments, we just run in a tight loop, but we still see performance impacts in the real world example. Let's put it this way. Okay.
And so does having this very optimized code within, say, a branched application or an application with these jumps, like where you're just sort of replacing these straight line segments with this optimized code, do those jumps have any sort of impact on, I guess, those performance speedups that you would get from this?
We don't really know, and no one really knows. So all you can do is pretty much benchmark the real world example with the state-of-the-art code and with our code, and you see that our code is 10% faster, 20% faster, 5% slower, depending on the machine and the primitive that you're looking at. So we don't know why that is. We don't know if it's always the case.
And it's a bit of a black box.
Yeah.
Okay.
But on average, we do see an improvement.
Cool.
And yeah, that's quite reassuring, I guess. The entire project is more or less to show that genetic improvement, that randomized search-based heuristics can improve the performance of code. And that is, now we need to see how widely is that applicable, how can we use that in industry, maybe.
Okay.
You mentioned earlier that you're starting from like JSON specification. You basically generate your own assembly code as a starting point. Just out of interest, have you tried starting from, let's say, the GCC or Clang assembly? Because that, I mean, it could just save you the first 1,000 mutations or whatever, but it could also be a much worse starting point because they do think completely differently, or just to get an idea, like how different the generated assembly actually is. I mean, is it likely that at some point you will generate something that's basically the same as what they do and then keep on mutating that, or are they going in a completely different direction?
Good question. We've done both. The problem with typical compilers is that they have a window in which they can optimize. So a typical compiler would maybe see multiplication 1 and addition 1 and see, okay, I can maybe shift that and I can save a spill somewhere there. But they're limited in the view of their peephole, as it's called in compiler lingo. We have not tried to pass the machine code from the compilers because the compilers already get they do get the C code, and the C code does not necessarily have all the information that I get. So for example, a carry bit can not be a carry bit in C code. It's always a byte. And then the compiler doesn't know that this byte is always just a 0 or 1 instead of 2 to the 8. Yeah.
It's really just that the C compiler doesn't have as much information as you have as a starting point. So it might actually start off with worse assembly because it doesn't have all the information.
Yeah. So these are two impacts that I have a benefit over, because I'm getting this C1 here is, or C0, whatever, is actually a carry bit and not a entire character. Yeah, and we view the entire function, the entire expression as a whole and try to implement that over just seeing sequence by sequence and then try to find patterns that are in my database of patterns that I try to optimize on. So instead of moving A to B and then B to C, I might as well move A to C. What did I say? Yeah. And these patterns are not something that I use to optimize. And the last thing is that the compiler not necessarily knows what exactly are the impacts of one particular optimization. So we do know that the -02 option of a compiler most of the time gives sufficient performance benefit, whereas the -03 option sometimes makes things worse, depending on the benchmark that you're looking at. By the way, we are comparing against -03 and native optimization, native instruction sets. So that is the best that typical compilers would be able to, utilize the hardware really. So I guess to conclude is that we have looked at the compiler code while we were slower than the compiler. Okay, what does the compiler do different and how can I get there? But at the time where we are better than the compiler does not really help. And we see at the optimization graph that, so from our overall budget, the budget that we are worse than the compiler isn't eligible. I don't know, maybe, probably. Important thing also to notice that we don't try to learn deliberately. We don't try to learn any properties of the CPU and try to apply that to a different CPU or try to apply that to a different curve or whatever. We are genuinely trying to, okay, this is what I have, and that can be anything. Let's see how fast we can run. I think that's a big assumption for this evolutionary computing in the first place. Maybe I'm walking on thin ice there, but maybe I should stop talking.
You didn't say anything about register allocation, or is there not much register pressure going on in these things?
There is. We look at the code. Where's the code? We see that, so side information, the mul_x instruction can multiply two 64-bit values and have a 128-bit result. R8 and R9 are the result registers, and Z is reading the value of Z from the memory. We don't see that mul_x is implicitly loading the second factor for that product from the register RDX. Okay, so that's prior knowledge that is specified in the Intel manual. For our second multiplication, which is here, we need to have, so the second multiplication is X, and X is read from here. That means that T0 must be an RDX in order to multiply, right? So that is a lucky coincidence that for this addition, I had the result of this addition, namely T0 already, the result for T0 already in RDX. So I did not need to move it into RDX. That is luck in this case, or I had this example so that it actually works. If RDX has a live value of something different, then I would need to move that out of RDX and move something else into RDX, and then and then do the multiplication essentially. I'm trying to be smart about that in the sense that that is somewhere here. So these are different multiplications now. So we have Z, so multiply 1 multiplies Z with X, and multiply 2 multiplies Z with Y. So it would make sense for this multiplication to put Z into RDX, so I can reuse that in both multiplications. And I do that, as we see down the lower right-hand corner. But this is not always that trivial to do. So I'm trying to, whenever I encounter an operation, then it is context dependent what I'm actually emitting on the level of instructions.
But because you fix the order, you can basically do the best job you can. Is that the idea?
Yes, the idea is that the optimizer will find that because a different register allocation makes the code faster. And that may be because there's less instructions. Sometimes instructions are for free. Sometimes instructions can be pre-fetched if it's from memory. Sometimes it's just instruction alignment. Sometimes the decoder. There's so many things that interleave with each other that affect the performance, which makes it just too hard to predict.
That also means, now I'm thinking about it, that if you run something 1,000 times, it's in level 2 cache or 1 cache. So that's not going to be very reflective of maybe what happens in the actual application, right?
Yes. So the
instruction cache will be there, but the data too will be.
Yes, but it's at the same
Memory.
same address.
Yeah.
Same memory address. For the instruction cache, we allocate 2 different pages and copy the machine code into these pages. So we're always page aligned. That's the best you can do, I guess. We've seen another paper where it's called doing things not obviously wrong, something like that. And depending on the environment, so which user is logged into machine, the benchmarks differ. And that is because the different user has a different user length within its username that aligns stuff differently, and that gives 5% decrease, increase. So yeah, that's, you try your best and then this is your results. Yeah.
Any last questions from Zoom, for example? Anyone from Zoom? Yeah, seems not. Yeah, but a lot of great discussion, and
yeah, thank you very much.
It's great to have all these discussions, and thank you very much, Joel, for your very interesting talk, and thank you everyone for tuning in. Hope to see you at the next seminar.
Thank you. All right.